All right, welcome back. So this is still Monday, the 16th, and I'm trying to just catch up on a number of different lectures. And I thought one of the ones I should definitely get to quickly is this lecture from Unit 9. This is the Advanced Color Theory topic lecture. And if you remember back in Unit 5, we had a lecture on painting, and I said painting would be the only art medium where it would be split in two. We had a lecture on painting in Unit 5 and then also in Unit 6. But I also said that the color lecture, which was in Unit 5, color, the basics, that would also be part one of part two. And I thought actually that part two is coming in Unit 8, but it actually comes in Unit 9. And so here we are. And so in this lecture, I'm going to go through this relatively quickly, partially because some of this, like the ambient and reflective color, some of that we already discussed in the first lecture on color, but we're just going to recap. And so to start with, let's recap a little bit. Let's see if my screen is awake. And just kind of think about the artwork that we have seen that we've talked about primarily in terms of color. Make sure that we're all familiar with um, the um, the three attributes of any color, which are three characteristics of any color, which are hue and value and intensity. And so here we're trying to demonstrate, although not working all that well on that scale, but on the green scale, pretty well, demonstrate what changes of intensity look like if there are no changes of value or as little changes of value as possible. And similarly here, we're doing a scale trying to show what does a shift in hue look like from a yellow orange. Yeah, from a yellow orange to a yellow green. What does that look like if it doesn't really change much in value at all? Okay. So at the end of the color basics lecture, we discussed just kind of briefly ambient color, the idea that the color of objects is not a thing that is fixed to the objects. Instead, the color of objects is always tied to what color of light is shining on them. So everything is affected by light, right? All color perception is fundamentally more about what light is shining than it is about what color any object is. And so some good examples of that are like the changes of temperature going on here, or like in the cast shadow on Elizabeth Vigée Lebrun's self-portrait up there on her face, right? How it's very, very warm because it's picking up the reflective light off the hat. Or a really good example also would be the way we're getting the reflective color on the side of the arms coming off of the robe, right? Um, that is also, I'm pretty sure, for those who are paying attention to guest spots in an artist's painting. So this is a Rubens painting, and I'm pretty sure that's Anthony Van Dyck who is there um, playing the role of one of the disciples, and once again wearing that really, really intense robe. I think Rubens just thought he looked really good in that robe. This is what I'm thinking. And so, but there's another issue related to ambient color, which is that color is affected by atmosphere. And this is true even in in a small space, like in a shallow space of a single room, like a single classroom, or even to a degree within a still life. But it's especially noticeable when we're outside and we're looking at landscape type space. So what happens with atmospheric perspective is that an atmospheric perspective is just kind of a subset of ambient color. It's just what it means when we say the logical system by which color changes and gets less intense as it goes further away. So when we're perceiving any color, we have to perceive it through a medium, that medium being the air that we walk through, the air that we breathe. And that medium also includes a lot of water vapor. And because of all the gases, all the dust particles, and all the water vapor, that means that every time we're looking at things through that medium, it is filtered and diffused and affected by that medium. And so, like, you can see that very clearly here, where the value contrast, the really strong value contrast of this dome is reduced, and that dome there has a slightly less intense amount of contrast, right? Because it's further away. Or just the difference between the contrast up here to the contrast back there, right? Okay, so there are rules about how atmospheric perspective works, but the most important rule is that the colors recede towards whatever the color of the day is, right? Like that if you think about it this way, that like at any particular time of day, any particular kind of atmospheric conditions, is it stormy out? Is there a lot of dust particle in the air? Is there a lot of water vapor in the air? For any particular day, those atmospheric conditions are basically going to set what is the color that represents the most distant view, right? And it's usually quite closely related to whatever the color is of the sky right around at the horizon line. And so all the colors of the stuff that we're looking at, right? Like if you think about like the boats, right? Like all these boats here and all the contrast we have there. And then as we look further and further back, they decrease in contrast because they're getting closer to whatever this most distant color is, which is probably something like that. And that means that they're going to reduce in value contrast. The darkest darks get a little bit lighter. The lightest lights get slightly darker. They're also going to reduce in color contrast and temperature contrast. And usually, for most days on planet Earth, it means that the colors are also going to get cooler. Not always. I have been in Los Angeles driving on the highway at around sunset, and I would tell you that the most distant color for that day was something more like a smoggy sort of orange. But for most places on this planet, at most atmospheric, most times a day, most atmospheric conditions, the color is generally going to be cool that everything is receding to. So here we have another example how we have richer and darker colors up close. Everything is in shadow. That's part of the reason. But then as we look into the distance, the colors get significantly lighter. And notice how the colors of the building are quite similar to the colors of the sky. This is John Constable, by the way, and it's a painting of Salisbury Cathedral. And for the longest of time, Salisbury Cathedral didn't look anything like this because for most of the 19th century, just collected all this soot from all the factories and everything in England. And so for most of the 20th century, the Salisbury Cathedral was pretty much black. I happened to see it right when it was in the process of being cleaned. So it is now a very similar color to this because it has been freshly cleaned. And by I say freshly, I mean within the last 20 years. So here's another example of atmospheric perspective. Notice how the saturation, right, the intensity of color, um, and the amount of contrast, the amount of value contrast is all greater up close. And then the further away we get, the more the color recedes to a color, something probably like about that. It's getting closer and closer to that distant, stormy, cool gray color, purpley gray color. Everything is getting more and more close to that color as it goes further away. And that means the darks are getting lighter, the lights are getting darker. Whereas here on the sunset image, the colors are shifting, but they're not necessarily shifting as towards cool. They are mostly shifting less intense and gaining a little bit of like a purplish, but the purple is more on the magenta side as they're moving away, right? There's also, because we're looking at a much warmer kind of distant color sky. There's another good example, also an American. By the way, so this painting, Heed, and this painting by Heed, right? Heed was an American landscape painter, part of the shoot, I'll think of it in a second. Um, part of the artists, of like of the 19th century who um the Americans who were just obsessed with landscape painting, and many of them who kind of stuck close to the East Coast, uh, like Heed and Innes, but some like shoot, he's on the tip of my tongue. He's not on this lecture. Oh well, we'll discuss him later. Getting back to Innes. So, also an American landscape painter, and look at how low intensity and how cool the colors get as we recede further and further away. The colors up close are warmer, more saturated. The greens are greener, they're richer, but they also tend to be more warm greens. Like there's also a lot more brown in a lot of the darks. And as we get further away, a lot of the dark values become more grayish and kind of grayish on the cool side. A lot of the greens shift towards more towards blue green. And if you look at both of these paintings, you get a sense of what I mean about how it's very specific to the time of day, right? Like what is the most distant color, the color that recedes into the distance is different for different atmospheric conditions and different times of day. Innes was truly an amazing painter. So another master of ambient color, both of atmospheric perspective, but of just also the idea that color is really very much dependent on the light situation and not on the object, and that's Claude Monet. And Monet did a lot of series where he would take the same subject matter and paint it again and again in different kind of atmospheric conditions. And he loved Rouen Cathedral. He because being a stone building and the stone was mostly light because it's like light gray color. It reflected whatever the color was of the atmosphere. And so the way he did these paintings was he had like a room set up where he could see the cathedral every day. And then depending on the conditions of the day, he worked on one painting or another. So like if it was a warm, sunny day and he started at 7 in the morning, he began with his early morning, warm, sunny day painting, right? And then he would switch to his mid morning, like somewhere around 9 o'clock, 10 o'clock, and then to midday painting somewhere around 11. And so he had paintings for each kind of time of day and each light situation, but also some paintings just for I woke up and it was really misty, or I woke up and it was raining. And so paintings for different atmospheric conditions. And I can't remember the exact number of versions of the Rouen Cathedral he painted, but it was a lot. Okay, so atmospheric perspective and how it relates to ambient color, that's one topic that I wanted to add a little bit more to in terms of advanced color theory. And one of the things let's go back just for a second, about this idea is that kind of relates to a topic that's come up again and again, both in the paint in the paper as I've been grading the papers, came up in the lecture I just did about perspective, which is what we see and what we think we see are not the same thing. And what we see and what we know are not the same thing. Like that, what we know about the cathedral is that it's a stone cathedral and it's stone colored. But what we see for any particular moment might be that the shadows are purplish or the shadows are orangish. Okay, so then another topic I want to talk about is just in the first lecture, we basically just talked about the color wheel as a starting model. And the color wheel, like the traditional color wheel, the traditional um, subtractive color wheel, which has primary colors of uh, red, yellow, and blue, is fine, right? Like you teach it to middle school students, you might even teach it to high school students. It's fine, it does its job okay, but it is not 100% accurate to what it is we actually see. And so there are different models that I want to talk about. Number one, I want to talk about the CIE, the chromaticity chart. And one of the main things I want you to notice about this is that there is a lot more space and room for greens. And the this actually makes a lot of sense because if you were to, as a painter, right, if you were to try to imagine all the possible greens that you could paint, all the changes of intensity, all the changes of value, all the changes of temperature, and all the combinations of different changes of value, intensity, and temperature of greens, cool greens, greens going all the way to very blue green, warm greens going very yellow green, but also dark warm greens, like dark brownish warm greens, olivey greens. If you can think of all those different greens, right? There's so many more possible permutations of green from like from yellow all the way to blue than there is types of orange from yellow to red, right? Does that kind of make sense? And so it should, because that's true, and like when you really think about it, it makes a lot of sense. It should also therefore make sense that the actual shape of the color wheel is not where the space from yellow to blue is just an equal arc as the space from yellow to red. It should, in fact, actually be a much larger section. And this is why we often talk about how green is kind of like the fourth primary color. And so the C.I.E. Chromaticity chart actually shows us why that's true. It shows us why there's so much room for our eyes to see green because there's just so many visible changes of wavelength of green that our eyes are attuned to. This is partially true because of, you know, where green is in the middle, right? It's partially true because how green and red are so close to each other. It's just the way our eyes are set up. But it's also important to think about as another challenge to the color wheel, like the other flaw. So one flaw to the color wheel is that it assumes equality. It assumes, like the traditional color wheel, it assumes that colors are equal distance from each other, that, that the distance from orange to red is the same as the distance from any green to blue or any green to yellow. And that's not true, right? And another flaw with the traditional color wheels is that they assume two-dimensionalness. They assume that all the color space is flat. And in fact, color space is not flat because it's really three-dimensional. And what I mean by that is because if there are three characteristics to every color, then the way all the colors interact also needs to be in three dimensions. So there are a number of different color theorists who have made models understanding the three-dimensional nature of color, but I don't think really many have outdone Munsell. I guess one of these days we'll have like a really good system that both combines all of what we know from the chromaticity chart and what we know from the Munsell color tree into one system, but we don't have that yet. And so in the Munsell color tree or color spheroid, what we have is a system where value changes on the vertical axis, right? So colors get lighter as they go up, and colors get more intense as they go out, right? So from the center outward increases the amount of intensity, but then colors change in hue as they go around. And that gives us three characteristics of color all in one three-dimensional model. And that therefore also explains and helps us to visualize what it means when we say that like a yellow orange cannot be high intense color at a dark value. There's no such thing. Notice the color is just not here. There's no such thing as, I don't even know how many steps this is. It's like 9 steps of intensity. There's no such thing as a nine step intensity color, right? For yellow orange at a value of a 2 or a 1. It doesn't exist. And similarly for blues or blue violets, there's no such thing as a high intensity color, super high intensity color at a light value. Or another way to say it is that the most intense version of each color is going to be at a particular value level. And so for yellow orange, it's going to be here at 8. And for this version of blue, it's going to be here at, what was that, at 5. So, and then my last point I want to make about color and how color works is that color is relative. Like our ability to perceive color is relative. And I'll show you that in a couple of ways. If you take a look at this Joseph Albers, especially, both of them are demonstrating this concept to a degree. But if you look at this one especially, and you look at how our perception of this color, the middle color, changes, how it seems to get darker as it gets closer to this edge, where it's now up against a color that's slightly lighter than it. And then it seems to kind of lighten as it gets close to that edge, as it gets closer and closer to this color that is just a little bit more intense than it, but also a little bit darker than it. It also changes our perception, not just of its value, but also of its hue. Seems a little bit more intense, a little bit kind of more reddish up here, and then it feels a little less intense and a little bit cooler here along the edges. And here's a chart that I made that kind of demonstrates this to a degree, how using colors to show you that like basically like this color and that color are the same color, but they don't look at all the same because of the way when they're surrounded by other colors, it changes our perception. Similarly, this color here and that color there are the same color, but they don't look like the same color. One feels much lighter, much warmer. Here is a student assignment that does the same thing. I'm trying to remember where are the good spots that demonstrate that. Um, Probably easiest if we just move on to the sketchbook assignments. In the sketchbook assignments, you can see, so like here is a shot, right? In these diagrams, this center grayish color is here and here are the same. Hold it. I had to sneeze. They are the same. And notice how it feels a lot cooler, a little bit darker, but especially a lot cooler, almost on the blue side here. And then it feels more kind of warm, kind of a yellow greenish version of that gray. And it feels a little bit lighter there. And on this chart, this color here and that color there are the same color. Notice how it feels much lighter here, also a little bit cooler. And here it feels a lot warmer and significantly darker. And then finally, I want to talk a little bit about optical mixing. And that's kind of like our last topic so artists have been interested in the idea of how to get colors to mix in our eye. I think once artists started to realize that we only have three color receptors, and that anytime that we're perceiving a color, we're essentially it's based off of optical mixing, whether we know it or not, in that it's based off of our brains taking the data from multiple sensors and saying, oh, this must be a yellow or this must be an orange based on how much my red and my green are, you know, hyperactive about this color. So, um, so Seurat was trying to trying to create that effect. So he tried to just using green, yellow, red, and blue, try to make, all the colors just with dots and dots and dots and dots and dots. But he couldn't quite make the dots small enough for it to really feel like true optical mixing. It's a massive size painting. It's a gorgeous painting. And it's a beautiful painting. But here we have some artists who are actually a little bit more successful at the optical mixing effect. So like in this painting, the base color never changes. It's always this kind of orangish yellow orangish kind of low intensity yellow orangish sort of color. It's always that color, but it changes based off of these other stripes, right? We get a completely different sense of the color that we're looking at as we combine both these stripes, which are in this kind of pale, kind of blue violet sort of color, with these yellow green stripes. And it really, so, and then also the change of width of the stripes and the way they also affect how we perceive the color. and a similar kind of effect here. And here are two artists that really kind of worked with optical mixing in pop art movement. And Arthur Honer is amazing. Like this section right there, there is no yellow in there. It's entirely made out of pinks, oranges, and these kind of like kind of RGB green with just a little bit maybe more on the yellow green side of RGB green. And just the combination of that green, that orange, and and that pink. And a lot of it, what he found was it worked a lot better if you kept the colors really light. And if you kept the base color, which is just very, very, very light kind of pearl gray, if you kept that color really, really light, and then it allowed for this kind of bleeding of colors, and you get more of an optical mixing sort of effect. Okay, I think that's where we're going to end for this lecture on the advanced color topics. And all right, thank you. Oh, Michaela, I didn't even know you were here. Do you have any questions before we end? Michaela, can you hear me? I got to type a question. Because you might be at work. Sand. I'll give you a minute to answer. If you have any questions, anything about prepping for the final exam, which opens up on Wednesday night this week and goes till Friday, or anything else that you have any questions about, um, quiz number 3 closes tonight. Not that I can answer much questions about quiz number 3. If you don't have any questions at the moment. All right. Well, then I'll end the lecture here. You have a good rest of your afternoon. I might do one more in the late afternoon before, but I'll definitely also be doing a 7 o'clock Zoom. And at the 7 o'clock Zoom, if I get like at least 2 people in it, we'll do a review for the final exam. Okay. All right. Speak to you later.